Well, just when you think you're done, I took a look at number 47 and remembered, oh, they also ask you about a confidence interval. So here's part 2 of number 48, which doesn't ask for a confidence interval estimate. But how would we use these numbers given to us to build a confidence interval? What is a confidence interval? It is in this case, the mean difference plus or minus some critical value, t star, times this would be the standard deviation in the difference, and then divided by square root of sample size. So that has to be adjusted for our two samples. So that's kind of a strange way to state it, but we have a better way to calculate this, right? This is replaced with this ginormous let's see, this is the variance divided by that plus, right? So when we add a second sample, we're adding variance, even though we're subtracting the means. And this is where that topic of combining means and variances plays such an important role in inference testing, inference procedures. Okay, so this is going to be a little bit different. Let me put the calculations on the other page here. So we are talking about a curve. Instead of putting the mean 0, though, we're going to put the mean difference of these two, 70.37 minus 68.45, which gives us 1.92 kilograms. That is our point estimate. And you could just say that. We looked at these 18 people, 10 skilled, 8 novice, and the difference between the mean weights was 1.92 kilograms. Done. Boom. Apparently, the experienced people have more muscle mass and they're heavier. But as a good student of statistics, you say, wait, that's the point estimate, but give me an interval estimate of that mean difference. That'll tell me how good your data is. And a sample size of 10 and a sample size of 8, really, those are pretty small. And then also, if you just take a quick look at these numbers, standard deviation of 6 and a standard deviation of 9, that puts you pretty far to the left and the right of either of those means. So you should be suspicious of just a point estimate and making a conclusion based on it. We are going to want to come up with a lower boundary and an upper boundary. The task here is a 90% confidence interval, giving us 10% tails. So we need a critical value that cuts off 5% at either extreme. You go to table C, you look up degrees of freedom 7. Why 7? We don't have the fancy, the fancy formula has been conducted for us, but it's hard to go to the table and look up 11.8. So I suppose if we wanted to, we could use the precise approximation and look up 11 degrees of freedom. But I'm going to use the conservative method, which is to take this n, the smaller of the two sample sizes, n minus 1 will give us our degrees of freedom. That's the conservative way to find p-values, especially when you don't have a calculator. Yes, we can punch these buttons in and get an answer. Let's take a look at how this actually works, though, using the math. So what number do I get when I go to the degrees of freedom 7 row and look up 5%? I get this magic 1.895 that I use on both sides. Of course, this one is over here to the left. Now, this is the critical value, so this is going to be multiplied by, maybe I shouldn't write those there. Let's put them in our formula, and then we will actually add and subtract. So, excuse me. We're going to call the confidence interval equal to this 1.92, that is our x bar of the differences, plus or minus, and here I'll put in our critical value, t star, multiplied times our standard deviation estimate. And you could go ahead and do S1 squared divided by square root of n, but let's actually use what they gave us, which is the standard error, right? So what I'm saying is you could do this, but they have already given us s divided by square root of n, so why not use it? Right here, this 1.929, but I am going to have to square it because that's the standard deviation divided by square root of n. So I would get back 1.929. So that's 1.929 squared. If you remember your Pythagorean theorem and hypotenuses of triangles, this is a little bit like we're not really adding the two legs to get the hypotenuse. We're adding the squares of the two smaller numbers. It will give us a bigger number, but it's certainly not just adding. What would we do? If we were novices, what would we do? We would just take the 1.929 and add it and get something like 5.1. So we are going to get something that's bigger than 1.9 and bigger than 3.2, but it is not going to be 5.1. So check this out. We'll put it in, 3.196. 3.196, that's a decimal there. Do the math, and this ends up being 3.733. So it's bigger than either one. I don't know if the hypotenuse example made any sense to you, but we square those, we add them, we take the square root, and then we get this combined standard deviation. And that, of course, is multiplied by our critical value. Critical value is how many standard deviations to the left and to the right? About 2, about 1.9. So this is going to be a little bit smaller than 2 times 3.7. And indeed, our margin of error here is 7.074. And let's bring this down. We've been saying this is the point estimate plus or minus. This is the point estimate plus or minus. And now let's actually do that math. So what do we get? We get an interval where the lower boundary is -5.154. Aha! A negative value is important. You were telling me that there's a mean difference of 1.92 kilograms. That is, the experts weigh more, are bulkier, are heavier, are denser in muscle mass, whatever it is. But wait, there's a really good chance, right? There's a 90% probability that this interval captures that true mean. And we don't know where that true mean difference is, but we're saying, well, it could be over here. The true mean difference could be, that the novices are 5 kilograms heavier. Or maybe it's way over here and the experts are, 7 kilograms heavier. We're not just saying that it's 1.92. We're saying that there is an interval, and the interval includes both possibilities of the novices being heavier over here. Here we've got heavier novices. Here we've got heavier skilled. And, the jury's out. There is not enough evidence to support the idea that the two means are different.